In section 11.7, we're going to look at a couple of other coordinate systems other than rectangular coordinates. The two most important sets are these: cylindrical coordinates and spherical coordinates. Let me introduce cylindrical coordinates first. There are three cylindrical coordinates: r, theta, and z. R and theta have the same rules as in polar coordinates. And z is just regular old z. So if I have a point in space, x, y, z, here's what r, theta, and z are. R is the perpendicular distance over to the z-axis. So r is the horizontal distance to the z-axis. If I drop this down into the xy plane, then I have a rectangle, which is standing up. Theta is the angle that that rectangle makes with the positive x-axis. And z is how high that point is above the xy plane. This should look like a rectangle. So to translate between cylindrical coordinates and rectangular coordinates, just like in polar coordinates, x is r cosine theta and y is r sine theta, and z is just equal to z. Since cylindrical coordinates are used to parameterize points in space, there are three coordinates. So since I can define any point in three-dimensional space using cylindrical coordinates, I have three cylindrical coordinates. Now, to get an idea of what this looks like, let's look at some examples. What are all the points in space that have r equal to 1? So these are going to be all the points that are at a distance 1 from the z-axis. Well, for any particular z-coordinate, the points that are 1 unit away from the z-axis are going to form a circle of unit 1. And since z can equal anything, this is going to give us a cylinder of radius 1 around the z-axis. So just comparing, if I write the rectangular equation for this cylinder, the equation is x squared plus y squared equals 1. If I write the equation for this very same cylinder in cylindrical coordinates, the equation is r equals 1. Notice that it has a much simpler equation in cylindrical coordinates than in rectangular coordinates. So in that sense, I'm going to say that cylindrical coordinates are better adapted to the cylinder. And if we want to carry out integrals, for example, on this cylinder, we're going to find out that it's much more efficient to do the integrals using cylindrical coordinates. Let's look at some other examples. In a previous video, I asked us to parameterize the cylinder x squared plus y squared equals 9. If we want to parameterize using cylindrical coordinates, here's the method. You start off thinking about about the general cylindrical coordinates? X equals r cosine theta, y equals r sine theta, z equals z. So I'm going to put that in a thought bubble. Then we substitute this into the equation which is given. So substituting in, I have r squared cosine squared theta plus r squared sine squared theta equals 9. So that's r squared times cosine squared theta plus sine squared theta equals 9. Since cosine squared plus sine squared is 1, r squared equals 9, so r equals 3. You then take that fact and substitute it back into the general cylindrical coordinates formulas. That will give us x equals 3 cosine theta, y equals 3 sine theta, and z equals z. Notice that by substituting r back in, I now only have 2 parameters left. Remember, when you parameterize a surface, you should only have 2 parameters. So my parameterization would be phi of theta and z is equal to 3 cosine theta, 3 sine theta, and z. Now, if you remember, when we parameterized this before using rectangular coordinates, we had to break the cylinder into 2 separate pieces, S1 and S2, and carry out a parameterization for each. Here, we can take care of the entire cylinder using just one parameterization. Here's another example. Let's parameterize a paraboloid. Let's do z equals x squared plus y squared. Let me change my picture. Notice that the paraboloid has circular symmetry about the z-axis. So using cylindrical coordinates around the z-axis is likely to give us a fairly simple parameterization. So once again, we'll start by thinking general cylindrical coordinates. X equals r cosine theta, y equals r sine theta, and z equals z. Now we know that that is not the parameterization for the paraboloid because there are too many parameters. Notice that there are 3 parameters here. R, theta, z. So that's not a surface. But if we substitute those into this formula, we get z equals x squared plus y squared. And in the previous example, we saw that x squared plus y squared equals r squared. So we have z equals r squared. We can then take that z equals r squared and substitute it back in over here. That will give us x equals r cosine theta, y equals r sine theta, and z equals r squared. So I'm replacing the z with r squared. And notice now I have 2 parameters, r and theta. So my parameterization is phi of r and theta equals r cosine theta, r sine theta, and r squared. Now this was not the only way of doing this. Another possibility would have been to say that r is equal to the square root of z. And I could have replaced the r with square root of z so that I had square root of z cosine theta, square root of z sine theta, and then z. And then my parameters would have been z and theta. But notice that then I would have had square roots in my parameterization. And I know that calculus is easier without square roots than with square roots. Let's maybe look at actually I'm going to split this into two videos since this one's getting long.